Hello, in this video we'll be solving this circuit and finding I3, which is what we want to find, using a variety of different methods: loop analysis, nodal analysis and superposition. I think so we'll start with nodal analysis, and that'll probably help do the loop analysis later. So let's label on these node currents. That's I3 already. Let's call this one I1, I2. Now notice I've drawn the directions of the arrows differently to how I drew them before. It doesn't matter as long as the equation is met, all currents going into a node sum to 0. So you can see this current's going in, but these two are coming out. As I1 splits up into I2 and I3, I2 plus I3 must equal I1. So we can write up here I1 equals I2 plus I3. So this is I2 here, because that doesn't go anywhere else, it comes straight through. This can be I4, and that can be I5. So I4 goes down there, I5 comes up here, same direction as this current source. So with that node, I4 must equal those two, because this one's coming out, these two are going in, those two can only go into this one, therefore I4 equals I2 plus I5. Now I5 has got to equal 2 amps because it's coming from this 2 amp current source. That's all that will be moving through there. So I5 equals 2 amps. We don't know anything else about these currents. Let's call this voltage Vn1 and that voltage Vn2. So what else can we work out about these currents? Let's find the representation of these currents as voltages and resistances. So that's flowing that way, so V1 will have to be higher than Vn1 to make that positive. So I1 equals V1 minus Vn1 over R1, which is 5 ohms. Let's put the values in, make it simpler, so that's 5 ohms. V1 is 6 minus, we don't know Vn1, over 5. I2 equals, it's flowing that way, so this one will have to be higher, so Vn1 minus Vn2, Vn1 minus Vn2 over 12. We don't know either of these. Sure, that's on the screen. Yeah. And I3 equals Vn1 over 3 ohms. 3 ohms. And I4 equals, well, that's higher, so Vn2 minus 8 over 15 ohms. These can be combined in there. Oh, and I5 we've already written there as 2 amps. Yeah, so these can all be combined together now. So V1, which is 6 minus Vn1 over 5 equals I2, which is Vn1 minus Vn2 over 12 plus, and this is 2i3, i3 is Vn1 over 3, Vn1 over 3, and separately 4, which is Vn2 minus 8 over 15 equals I2, which is 2 amps. I5, which is 2 amps, plus I2, which is Vn1 minus Vn2 over 12. So with these two equations, simultaneous equations, should be able to work out Vn1 and Vn2. So these two are equal, these two terms are equal. There's a Vn2 here and Vn1's otherwise. Not a very useful thing to find. Let's leave those. Let's not make those equal. Rearrange one of them to be in Vn terms of Vn2. Let's rearrange a second one. So Vn2 equals, move this to the other side. So 30 times 30 plus 15 over 12 Vn1 minus Vn2 and then move that minus 8, so plus 8, so that would be 38. Get rid of that. There's still this Vn2 here. We want that on the other side. So Vn2 plus 15 over 12 Vn2 equals 38 plus 15 over 12 Vn1. Therefore, that also equals 15 over 12, 27 over 12 Vn2. Just combine those together. And I will move those. Which one do we want to find out? We want to find Vn1 because we want to find I3. So Vn1 is most important. So this was the right thing to do. Find it in terms of Vn2, and we can put that into this first equation. Let's move that bit to the other side. Therefore, 12 over 27 times 38 plus 15 over 12 Vn1 equals Vn2. Now we can put this into here wherever Vn2 appears and rearrange to find Vn1. So 6 minus 12 over 27 6 minus 12 over 27 is this bit, so 38 plus 15 over 12 Vn1 over 5 equals, run on down here, Vn1 again, so 12 over 27, 38 plus 15 over 12, Vn1 minus Vn, sorry, this is Vn2. I only need to put it in here. That's a mistake. It doesn't make any sense anymore. Putting Vn2 in here, so 6 minus Vn1 over 5 equals Vn1 minus 12 over 27, 38 plus 15 over 12 Vn1 over 12. So that would cancel with that. That could go over there. Plus Vn1 over 3. So I want to move all the Vn1s to one side. So let's do that. Do that in this space here. Knock that off. So let's leave the Vn1s on this side and move the numbers to the other side. So 6 over 5 plus 38 over 27 from here equals, I'll move that to the other side, so Vn1 over 3 plus Vn1 over 5, that's these two, and then there's this Vn1 over 12 plus Vn1 over 12, and there's one more term, it is plus that, so that can get rid of that, make that a 1. That's the over 12, so 1 over 27, so 15 over 12 times 27, 12 times 27 Vn1. Move back into this space here, it's getting a bit cluttered. Vn1 equals 6 over 5 plus 38 over 7, 27, 38 over 27. All of these terms can be taken out in front and multiplied by 1 over 5, 1 over 3, 1 over 12, and then that can be moved to the other side. So these multiplied by that's times, divided by, sorry, that's why I did that in the first place, 1 over 3 plus 1 over 5 plus 1 over 12 plus 15 over 12 times 27. And that can be put into my calculator. We get a number. Six over 5 plus 38 over 27 over 3 to the minus 1, same as 1 over 3, plus 5 to the minus 1, plus 12 to the minus 1, plus 15 over 12 times 27 equals almost 4 volts. Equals 3.933 volts. So once we've found that, we can find I3, because, so let's use this space here. V equals IR, therefore I equals V over R, which equals 3.933 divided by 3, which equals, divide that by 3, 1.311 amps approximately. So that was finding I3 by nodal analysis. Now let's do loop analysis. I'll do superposition last. So that's about right. Let's make some loops. So let's take this loop this way and that way. Same with this loop and this loop. Let's call that VR1. Let's make that point the same way as the loop. There we go. VR2 and that VR3 goes that way across there. So sum these voltages. V1 plus VR1 minus Vn1 equals 0, and Vn1 plus VR2 minus Vn2 equals 0, and Vn2 plus VR3 minus V2 equals 0. Put the numbers in later. The two numbers we know, V1 and V2. Now we need the equations for current. So that's out over here. I1 equals VR1 over 5, we know that. I3 equals Vn1 over 3. I2 equals VR2 over 12. And I4 equals VR3 over 15. And I5 equals 2 amps. We know that already. And we also need these equations again. So let's put those into these equations. Separate that off. So VR1 over 5 equals VR2 over 12 plus Vn1 over 3, and that's that one done. And the other one is VR3 over 15 equals VR2 over 12 plus the I5, which is 2 amps. 2. So we're done with these. We need these. We need these. So these can be rearranged and put into here. So we want to get rid of VR2, and we want to get rid of VR1. Out of these three, there are 2 containing VR. Yeah, let's just do it. There's space down here. That's about frame right. So we want to rearrange these. That's known. That's what we want to find. Rearrange this one to make VR1. So VR1 equals Vn1 minus V1, which is 6. and this one. Let's use that straight away and put it in one of these. So VR1 doesn't appear in here anyway. Just put that in this top one. So this becomes Vn1 minus 6 over 5 equals VR2 over 12. Well, let's find VR2 first, and we can put that in there as well. Let's move those across. So VR2 equals, and that goes over there, Vn2 minus Vn1, which isn't known. So Vn2, here Vn2 minus Vn1 over 12 plus, I think that's Vn1, yeah, Vn1 over 3. That's what that one becomes. So now we need to find the equation to find R3, to rearrange this last one. V R3 equals, now we'll move to the other side, V2 is 8, 8 minus Vn2. 8 minus Vn2 goes in place of there, so that becomes 8 minus Vn2 over 15 equals VR2, which is this here, over 12, that's the same, Vn2 minus Vn1 over 12 plus 2. And if we look at what we wrote here before, find these two equations. Okay, these two equations are the same as these two equations, unless I made a mistake, which I have somewhere in one of these two, because that is minus that opposite way around. That's the opposite way around, and that's positive. So if it was all negative, it would be the same, because you could just times everything by minus 1. That's negative and that's negative and that's not. It means that one of these is wrong. That's negative, that's not. Unless the voltages are defined differently. I don't think they are, so we use the same schematic. Anyway, the process then is exactly the same as what was done here to find I3. I've just gone about it in a slightly more long-winded way. There was this much working before, finding these with a nodal analysis, and all of this with a loop analysis. And I think that's all I'll do for this loop analysis. Which one's right? I'll get back to you on that one. So I had a little look at it, and I found out which one, where we went wrong, and that was with the direction of the currents. When I did loop analysis before, I said you would be very careful to look at the direction. This current's moving in, this voltage is across the wrong way, so that would be a minus. So anything with an I4, this would be a minus. This is features VR3. VR3 was this one, so this would be minus, because that I4 would be flipped, because that's pointing the wrong way. I2 would also be flipped, I1 would also be flipped. So I2 and I1 are just the other currents, so that one minus and that one minus, and that one minus. Those two are the same. Those three, 1, 2, 3, will change round. Now that's exactly the same as this. So on to superposition, and now we can redraw this circuit 3 different ways, with these 3 being removed and only 1 left behind, so we can work out the current contribution, I3, which is of course what we're looking for. So let's remove the current source, and that 8 volt voltage source. Look at V1. If we do that, we find that that's a short circuit and that's an open circuit. So these two are in series, parallel with that one. And we're looking for I3, so we can't really collapse it anymore. So we can draw that out as, let's do it down here, 5 ohm resistor, 5 ohms, and we're looking at this voltage here. This is 3 ohms, and this is in parallel with this resistor, which is made of these two in series, add together, so that would be 27 ohms. 7 ohms, and that is 6 volts. And we're looking for the current flowing into here. I think the easiest way of doing this without using current division is to find out that voltage there, VN1. In fact, I think the easiest thing to do would be to find on the screen. There we go. Easiest thing to do would be to find VN1 for all three, add them together, then find the current out afterwards. We did for this. Hopefully the answer will be the same. So the current for this one, we can put this straight into a calculator. Got 6 volt and a potential divider again, so the voltage VN1 equals 6 times 3 in parallel with 27. That's a symbol shorthand for parallel with, divided by 5 volts, that resistance there, plus 3 in parallel with 27. We can do that on the calculator. It doesn't have a parallel with button, unfortunately, but we can use the times and divide method we used before. Times 3 times 27 over 3 plus 27 over 5 plus 3 times 27, 3 plus 27, and that equals 2.1. So VN1 1, I'm going to call that because this is only the first stage, it's not equal to VN1 quite yet. VN11 equals 2.104 volts. And let's draw out the second circuit diagram we can make from this. Let's make V1 short, keep this, get rid of that. So then we have these two in parallel. So that's 5 ohms and that's 3 ohms, and we're looking at this voltage here, Vn, and that's 12 ohms there, 12 ohms, and then there's the current source, another resistor here, which is 15 ohms, and that's 2 amps. I think the easiest way to work this one out would be to work out the current going this way out of here, and from that we can work out the voltage made across here, which would be the current times the resistance of these two in parallel. So to work out the current here, I'm going to have to work out how much of that 2 amps will be split between there and going through this 15 ohm resistor here. So to do that, we'll first work out what the impedance of this bit is. So that's 5 in parallel with 3. Let's do that on the calculator. 5 times 3 divided by, that'll still work, 5 plus 3 equals 1.875 ohms. This bit's equivalent to 1.875 ohms, and that's 12 ohms, so that whole leg will be 13.875 ohms for this whole bit here, and that's 15 ohms. Now current division works a little bit differently from voltage division, because current would rather take the shortest path. Voltage would rather be on the largest resistance. Current would rather go through the smallest resistance. When you're calculating using current division, you use the opposite resistance to the one you want to know the current through. So we've got this current here, but we want to use the 15 ohms instead. So it would be 2 times, we want the 15 ohms over the sum of the two, 15 plus 13.875. That's telling us 1.04 approximately amps is going that way, and the impedance here is 1.875 ohms, and that current's going that way, so we should get a voltage across there of 1.04 times 1.875, 1.04 times 1.875, 1.95 volts. V12 equals 1.95 volts. Now on to the third to calculate is the voltage across here. Let's get that on screen. Voltage across here with this supply, so that one gets removed. We've got this large resistance here, and then these two in parallel. Let's draw that out. Let's draw that out up here. So we've got, we know already that those two in parallel is 1.875 ohms, and then we want to know the voltage on there, and then in series with that we've got the 12 plus 15, which is 27 ohms, and an 8 volt source there. Third VN1. It's across there. So this one's a very simple current division, voltage division, sorry. We want 8 times 1.875 over 1.875 times 27, which plus 27, which equals 875 divided by 1.875 plus 27, 0.519 volts. So then we add these three up, 2.104, 1.95 and 0.519, and we get 3 going 1, 7 going 1, 6 going 1, 1, 2, 3, 4, 4.673. 673 volts. Now that's different to the answer we got before, 3.993. I noticed that earlier. There's the answer we got before for the voltage, 3.993. It came out down here. Noticed that before, and there was a mistake made here. See this minus sign here? That of course also applies to this when we take out those brackets. However, on over here we had this is a positive, whereas that shouldn't be a positive, that should be a negative, and so that should be a negative here, and hopefully then we'll get the right answers. So this can be a good reason for using more than one method. You can double check your work, and a lot of exam questions will have do this and then check it with another method. Often I'll tell you which method to use. So 6 over 5 plus 38 over 27 over, let's do the to the minus again, 3 to the minus 1, 5 to the minus 1, plus 12 minus 1, minus 15 over 12 times 27. This time we get 32 over 7, 3.571 there, and there's the answer we got before. It's closer. We didn't do any rounding here, but we did do rounding here, so that might be part of it, or we might have made another mistake. But anyway, that's the three methods. So the big mess you get from loop analysis, and then you end up with the same as you would from nodal analysis, with just a small amount of working, and there's a lot more working to cajole that into the form you want for finding whatever you're wanting to find. Obviously it would be slightly different if we wanted to find, say, Vn2 or another current somewhere else. And superposition can be a lot easier. This took a hell of a lot less working, and we were able to just put it straight into a calculator. So superposition can be quite handy to check things. If you can spot where I went wrong and where I got the two different answers from, please put that in the comments. But thanks for watching. Bye.